This is the tutorial session number 7, and we will go through these two problems that has been posted onto Blackboard. So problem 1 is a CNV system. We will first look at the problem statement. It says a restaurant is air conditioned using a CNV system, as you can see here. So we have this restaurant. Summer design condition is 24. So this is a design condition for the restaurant, and the space sensible load and latent load are given, which is 40 kilowatts and 10 kilowatts respectively. And we do know that the off-coil air state at point C is constant, so we can find point C, and its condition is 14 degrees and 90%. And the fan duct heat gains can be neglected. So first we will look at this CFV system here. So we have outside air coming in, and we have this is so printed version here is not that clear. So we have, you can see that the arrow represents the direction of the airflow, and we have outside air mixed with the return air, and then it goes through a cooling coil. And no matter how the outside air condition and the return air condition changes, this state C is at a fixed condition, which is 14 degrees and 90%. And then the conditioned air will be supplied into the system. Before it's powered by the fan, we can see that we have a bypass damper that might open. So if the bypass damper is open, then some part of the return air will be mixed with this state C and then be supplied to the restaurant. So first of all, you're supposed to determine the design supply air volume flow rate and the space relative humidity at the design conditions. So you are supposed to design the volumetric flow rate and the space relative condition. So we can see that it's a pure space air conditioning problem. So at the design condition, obviously, the bypass damper will be closed. So it will be 100% supply. The supply air will be 100% the airstream that is after the cooling coil. So uh, since the fan and duct heat gains are neglected, so our supply S or S condition is our equals our state C, and you're supposed to find the space relative humidity. So you would like to know or locate the R condition. And in order to do that, we do know that for space latent load, Q sub L latent load from our lecture notes, we know that it's actually equal to the mass flow rate of the supplied air times omega, delta omega. In this case is the humidity ratio at the return state minus the humidity ratio at the supply state, and then times the latent heat of water at 0 degrees. So from this equation, this is a known value You can easily look this up on psychrometric chart because here our state S is state C, and for our state C, it's a constant state at 14 degrees, 90% 90% relative humidity. So this is a known value, and this is a parameter, a property value. So this is also a known value, and this is also a property value. So the actual density of air will be given in exam problems, and you are left with the volumetric flow rate. So in this equation, our latent heat or latent load is known, which is 10 kilowatts, and air volume flow rate is unknown, and this is what we need to calculate. So if we can calculate the supply air volume flow rate, then the humidity ratio of the return state or of the design state can be fixed. And combined with the 24 degrees design temperature, you can easily find the relative humidity. So this is for relative humidity. And then we will be looking at how we can find the design supply air volume flow rate. So it's also very simple. So what we do is we know that the sensible load equals density times the air volume times Cp of air times return temperature minus supply temperature. So this value, or on the left-hand side of the equation, equals 40 kilowatts, as stated here. And then this is a known property value, the same reasons here, and this is what we would like to know. Okay, and Cp of air is a property value, and temperature of the return air is the design temperature, which is 24 degrees here, and the supply temperature equals the temperature at state C, so it's 14 degrees. So we can see that for this equation, the only unknown is the air volume flow rate here. So once you have fixed the air volume flow rate, you plug in the number to this equation, and then you can fix the humidity ratio value. And combined with the design temperature, you can easily find the design space relative humidity at the design conditions. Okay, so this is for problem number 1. I'm not going to guide you through the detailed calculation, but I'm going to post the detailed solution after this session. Okay, so that's for question number 1. And for question number 2, if both the space sensible and latent load drops to 70%, and you're supposed to determine the required supply air temperature and volume of the bypass air. So you can see that in the problem schematic, we have a bypass damper here. So if the load, either if it's sensible load or latent load drops, then if we supply 100% of the off-coil air state, the room will be overcooled. So that is why you can see here, part of the return air will be bypassed here, whereas the remaining part will be supplied back to the outside. And as you can see here, the fan is a constant. This is a fan for CFV system. So this volumetric flow rate here, this stream, will be maintained at a constant value, and this value is actually the value of our air volume flow rate we have already determined in question number 1. So the final value here is 3.268 cubic meter per second. So this is volumetric flow rate of the supply air. Then this value is 3.268 cubic meter per second. And then we have a bypass volumetric flow rate. And we have a coil volumetric flow rate. So we have stream number 1, stream number 2, and these two numbers added up together equals this number. So this is the first equation we get. V sub S equals V sub coil plus V sub bypass. So this is the first equation we get directly from mass balance. And then what we do is we apply the energy balance for both of the latent heat and sensible heat. So here, our partial sensible heat equals 70% of our actual sensible heat. So it will be 0.7 times 40 kilowatts. Then on the right-hand side, it will be density times volumetric flow rate of the coil side. And the reason is when bypassed air is supplied into the back into this air-conditioned restaurant, since the air state of the bypass stream is the same as the air state in the restaurant, so it will not take care of any heat load, including sensible heat load or latent heat load. So this is the reason why when we apply this equation here, then V dot coil, this volumetric flow rate will be equal to the stream of the airstream right after the coil. Then it will be T temperature of the return air minus temperature of the coil. So this is that, and we know that the temperature of the return air is maintained at 24 degrees. As you can see in the problem statement, it says you need to determine the required supply air temperature and volume of bypass air to maintain 24 degrees indoors. So this is 24 degrees. And the temperature of the off-coil airstream is still 14 degrees. So when you compare this equation with this equation, you will see that the left-hand side is reduced to 70%, and the right-hand side, all of the other parameters remain the same, including the density, specific heat, and temperature difference. So therefore, V dot coil equals 0.7 V dot S that we have already calculated here. So combining this equation and this equation here, we know that V dot coil equals 0.7 V dot S. So Therefore, substitute this equation to the first equation here, then our bypass volumetric flow rate equals 0.3 original total supply air volume flow rate. So this is for the first sub question. And secondly, you're also asked to find the space relative humidity at this condition. So what we do is we apply the latent heat transfer. So at partial state, there's no room for me to write the equation here, so I'm going to write here. So the partial latent load equals the similarly equals density times the coil flow rate times the humidity ratio at partial state minus the humidity ratio at supply state times HFG. Okay, so we can see here the left hand side. For the left hand side, this value becomes 0.7 or 70% of the latent heat value, and this constant remains the same. And V dot coil, as you can see here, V dot coil equals 0.7 V dot S. So comparing this equation, the latent load at a design state, and this equation, latent load at a partial state, we will see that this value actually the humidity ratio at the partial load equals the humidity ratio at the design load. And then since the temperature is also maintained at 24 degrees and the humidity ratio also maintains at the same value here, so the space relative humidity at partial load equals the space relative humidity at the design load. So this is for problem number 1. So the important key points are, first of all, you will need to understand the mass balance at here, before the fan and after the fan. And secondly, you will need to understand how you can calculate the space sensible load, latent load, and also space sensible load at partial state when we have bypassed air, and space latent load at partial load conditions. We will also have bypass air. So this is for the first problem. Okay, so if you don't have any questions, then we'll be moving on to the second problem. So for this second problem, we have a classroom, also a air-conditioned classroom. And now the system is changed to primary air fan coil system. So the primary air fan coil system means we have a primary air handling unit for the whole building, and we have fan coil system for individual rooms. And for the air coming right out of the primary air handling units, the state is the same for different rooms. So we have here at summer design condition, space sensible and space latent loads are given here. And the amount of primary air supplied to the classroom is given. and the supply air from the fan coil unit is also given 14 degrees and 90%. And the fan heat can be neglected. Okay, so let me see. For the sub questions, first you are supposed to determine the supply airflow rate required to maintain the indoor temperature at 24 degrees and the resulting indoor relative humidity at summer design condition. And if the primary air is at 15 degrees at the same moisture content, and sketch the psychrometric cycle and determine the sensible latent load fan coil unit. Okay, so what we will do is first we will calculate question number 1. So for question number 1, determine the supply airflow rate required. So the indoor temperature is at 24 degrees. So first of all, we will apply the sensible heat load calculation for this fan coil system. So our sensible heat, the same equation equations here. Our sensible heat load equals density times the supply air flow rate times the Cp of air times the temperature difference. And for temperature difference, it's referring to the return air temperature minus the supply air temperature. And for this problem, the sensible heat load is 6.8 kilowatts. So this is a known value, and these two values are known. And return air is our design air temperature, so it's 24 degrees. The supply air, you can see here, supply air from the fan coil unit is 14 degrees and 90% saturation. So it's 14 degrees. So therefore, the only unknown is the supply air flow rate, and it's calculated to be 0.55 cubic meter per second. So first of all, we have determined the supply air flow rate required. And then you will need to calculate the indoor relative humidity. So the method is the same as here. We have latent load calculation equation, density times airflow rate times humidity ratio difference times HFG at 0 degrees. And our supply humidity ratio is given because our supply air temperature and relative humidity is given. So this is known. And the return air humidity ratio is the only unknown, and it's calculated to be 0.0099 kilogram per kilogram dry air. So that's for the first question. And for the second question, it says if the primary air is at 15 degrees and having the same moisture content as the room air, and you will need to sketch the psychrometric cycle and determine the sensible and latent load on the fan coil unit. So then of all, we draw a arbitrary psychrometric chart, and we have a return humidity ratio here. Okay, so for our return air, the temperature is 24 degrees, and so we have temperature is at 24 degrees. So this is our return air state. And then we know that the primary air is at 15 degrees. So primary air is in the left-hand side of our return air, and it has the same moisture content as the room air. So our primary air will be somewhere here. So it will be 15 degrees and with the same moisture content. Okay, and you're supposed to sketch the psychrometric cycle and determine the sensible and latent load on fan coil unit. So then what we do is, first of all, we know that for the total supply air flow rate, the value is 0.555. And we can see that this value is actually larger than the amount of primary air supplied into the classroom. So that means part of the room air will be returned back to the fan coil units. So we have a state M here. We have, first of all, a mixed state between the primary air and return air. And this is only a sketch, and actually you will need to determine the actual location of this M dot. Depends on the actual primary air volumetric flow rate and the overall total supply air flow rate. Okay, and then our primary air will be treated to supply air condition. For supply air condition, we look at the problem statement, and it states that the supply air from the fan coil unit is 14 degrees and 90% saturation. So it will be somewhere here. So then it will be treated to supply air, and it will be supplied back to the return air. So this is what it looks like. Our primary air first mixed with the return air, and the mixed air will be treated to supply air, and the supply air will be supplied back to the room to follow the space air conditioning process SR. Okay, so this is for the sketch. And then you're supposed to determine the sensible and latent load on the fan coil unit. So basically, you apply the same equation, but between state M and state S. Okay, so the third question, comment on the required coil's latent load in part 2 and any potential problems. So this seems to be taken care of once you have calculated the required coil's latent load. So basically, since the primary air first here, primary air humidity ratio equals the humidity ratio of the return air. So the room latent load equals the fan coil latent load, as you can see in the schematic here. So as we know that for fan coil, if you would like to treat the latent load, the only way for you to do that is by supplying, by condition the air with a wet coil. So that means with a cooling and dehumidification process. And the fan coil unit is quite different from the air conditioning unit, from the air handling units. So if we are going through, if the air is going through a cooling and dehumidification process in the air conditioning, in the air handling unit, then we have special pipes that can drain out the condensed water. However, our fan coil unit is installed inside the room. So if we have large amount of condensation occurring inside the fan coil unit, it is possible that some water will be leaked to the if it's the ceiling or even to the inside of our room. So this is the potential problems. And to avoid this problem, as you can see here, what we can do is we can further treat the primary air in order to make sure that the humidity ratio of the primary air is smaller than the humidity ratio of the return air. We also have booked this room. So this is our regular tutorial session every Tuesday. Maybe you can contact our general office. Okay, so this is for question number 3. Before I end, I would like to draw your attention on the group project. I have received a lot of emails regarding the group project. So first of all, I will need to reiterate that this is not a mini design project. So the major work that you will need to do is to first of all analyze all the characteristics of the load in each room, and then zoning this office building and design the individual air conditioning process for each of the zone, and then determine this, including determining the supply air temperature and construct air conditioning process and etc. So as you can see that the CAD drawing, AutoCAD drawing is not required, and also the Energy Plus is only an option. So it comes to my notice that Karen has not guided you through the all the actual demonstration of how you can actually use this software. So I have talked to the our associate head for teaching, and he said he arranged it this way. So you're supposed to learn that next semester. So this is not part of the learning material and learning scope for this course. So you're only supposed to learn the energy, how to use Energy Plus next semester for your actual design process, and Karen will demonstrate how to exactly use the Energy Plus software next semester. So regarding this situation, estimating the cooling load for all year or for a different times during a day is not required, but you will need to estimate the design cooling load. And also you will need to, because there are some information that might not be adequate to carry out the actual cooling load estimation. So you have to clearly list out your assumptions and make sure that you have made the reasonable assumptions. Okay, and all that materials will need to be presented in PowerPoint in a presentation in I think week 12. So to sum up, this is not like a design project where you are supposed to look up all the product category and find a equipment or draw out the AutoCAD drawings. But the work here, scope of the work, is really related to the course materials that we have already covered. Okay, so this is for the project. So I'm going to stop recording